Good stuff right there. A little bit of a piano solo from Magic Mirror and Leon Russell. Good morning. Uncle Lee here with a little trigonometry discussion. Before we start that trigonometry discussion, let's have a little review about a function we would call quotient function. H of x is equal to f of x divided by g of x. Now that could be a rational function if f and g both were polynomials, or it could just be a quotient function. Maybe f is a transcendental function, maybe a logarithmic function or a trigonometric function. So, but what we're talking about here is going to apply for any quotient function. If I have a quotient function, the domain is going to be easy to find. The domains happen when x, bottom, g of x does not equal 0. You can't divide by 0. We're doing analysis of functions of real numbers. So you cannot divide by real numbers in the realm of, you cannot divide by 0 in the realm of real numbers. So that's going to be the domain of our quotient function. The range takes some investigation after we get the graph. You just can't really see what the range is. And for the example we're going to talk about today, you'll see. Where are the x-intercepts of a quotient function? These are all topics that we discussed in our study of rational functions last semester. When is a fraction 0? A fraction is 0 when the top is 0 and the bottom is not. Top 0, bottom not. That's when h of x is equal to 0. That's when we have the x-intercepts. When f of x is 0 and the bottom is not. What happens, let's again go back to those values in the denominator that are 0. What happens if the denominator is 0 and the top is not 0? We saw that if the top was 0 and the bottom not, those are x-intercepts. That's where the graph crosses the x-axis. But what about when f of x does not equal 0 and g of x does equal 0? Those values are not in the domain. Well, for those x values, we have vertical asymptotes, something else that we talked about when we studied rational functions. So where is all of this leading us? This is leading us to a very nice discussion. Oh, sorry, slow your roll a little bit. Something else that we're going to need in today's lesson, a note about increasing, decreasing. And this seems so obvious. But it's something that we need to completely wrap our heads around, especially when we start talking about series and when we're in Calculus 2 and things of that nature. It's going to help us today in thinking about the graph of cosecant. And that's where we're going. We're going to graph the function of x, cosecant x. Think about this. 1, 2, 3, 4. Those are increasing values. Increasing values. True or false? If I take a set of increasing values and divide those values, or take 1 and divide 1 by those values, 1 divided by 2, 1 divided by 3, 1 divided by 4, then I have a set of values that are decreasing. So if I have a set of increasing values, 1 divided by those increasing values will give me a set of decreasing values. That's going to help us a lot in our discussion of the graph of cosecant x. What the heck is cosecant x? Basic identity. Well, by definition, cosecant x is 1 over sine of x. Not sure why I'm calling it g there. Let's call that as what it is. That's just another word for f of x. If f of x is cosecant x, then f of x is 1 over sine x. The first thing you need to realize is that cosecant x is a quotient function. It is a quotient function, and it's going to have all of the properties that we just discussed of a quotient function. Well, the first thing we always discuss when we have any function is talking about the domain. So there may be restrictions to the domain. Well, what would be those restrictions on the domain? You can't divide by 0, so therefore the bottom of this quotient function could not be equal to 0. So we're going to find out where the bottom 0, i.e. where is sine x 0? Where does sine x equal 0? Where does sine x equal 0? At 0 and pi, at 0 and pi. We're going to come back to our unit circle a lot. And keep in mind the sine values are the y values of the points on the unit circle. And we see if the angle measure is 0, sine is 0. If we go over here to pi, then yes, of course. If I go over here to pi, the sine of pi is 0. Well, and look at this. The sine of 2 pi is 0. Sine of negative pi is 0. So think about that. Those are all, and you know that. We've talked about the sine graph. We've talked about the period of the sine graph and where it zeroes out. So that's nice. That gives us nice values, a nice way to think about the domain of cosecant, which is 1 over sine. Well, that's going to be, what is the domain? It's certainly at 0 and pi. And if you think about that, it's going to be 0 plus any integer multiple of pi. And this is hard for elementary math students to think about, to write. In my experience, it has. But some students, oh, I get this. I get this. It's not. Just think about it a little bit. So at x equals 0 plus any multiple of pi, where n is an integer, that's the anti-domain of cosecant. Those are the values not in the domain. And you could, what is 0 plus n pi? So the domain of my cosecant function, all x such that x cannot equal n pi where n is an integer. What happens at those values? What happens at those values? Think about that for a moment. Think about our discussion on quotient functions. If the bottom is 0 and the top is not, bottom 0, top is not, bottom 0, top is not, what do you have? You're darn right. What happens to the graph of x there? What happens, you're darn right. The bottom 0, top not, we have those explosions, those vertical asymptotes there. That's what's going to happen. You have those asymptotes, wherever any multiple of pi. You're going to have some explosions there. Let's look at those. So, and I have this, I have an xy plane. We're going to graph it, of course, on the xy plane. And wherever I have 0 pi, 2 pi, 3 pi, negative 2 pi, I'm going to have vertical asymptotes. And I have those sketched there in dashed yellow lines. Very nice. So that's the first part of the cosecant graph. So what do I need to do? I need to figure out then what happens to cosecant between 0 and pi, between pi and 2 pi, between 0 and negative pi. What happens? Well, let's do some investigation there. Let's find the x-intercepts. Cosecant is 1 divided by sine x, and we know a fraction is 0 when the top is 0 and the bottom is not. That's when a quotient function is 0, when the top is 0 and the bottom is not. When is cosecant 0? What are the x-intercepts of cosecant? Well, they happen when 1 is when 1 is never 0. The graph of cosecant will never cross the x-axis. It never has x-intercepts. Never has x-intercepts. 1 is never 0. Key point. And if most of us had a pretty good foundation on rational functions, this is just an extension of that discussion. This is not a rational function. It's a quotient of some transcendental things going on, but it's still, the same rules apply about quotients. Let's see what else we're going to discover here. Well, this never has x-intercepts. Never has x, it has no x-intercepts, cosecant graph. We just talked about that. So we have no x-intercepts. So what, no x-intercepts. So what can we do? Let's think about sine between 0 and pi. Between 0 and pi, let's think about sine. Well, between 0 and pi, the y values, y1. Here, that's a nice one. Right at pi over 2, the sine of pi over 2 is 1. The sine of pi over 2 is 1. Oh, that's nice. Therefore, what's, hey, oh, and cosecant is 1. At x equals pi over 2, the sine of pi over 2 is 1. So what is 1 divided by sine of pi over 2 is 1. So therefore, cosecant of pi over 2 is 1. Nice. That's very nice. Hey, what about at x 3 pi over 2? What about 3 pi over 2? 1 half, 2 half, 3 pi over 2. The sine is negative 1 half. Oh my goodness gracious. So therefore, the cos at x equal 3 pi over 2, the sine of 3 pi over 2 is negative 1, so what the heck? Cosecant of 3 pi over 2 is 1 divided by negative 1. 1 divided by negative 1. Let's plot those points. Let's plot those points. At pi over 2, I've got a 1, and at 3 pi over 2, I've got negative 1. Let's plot those points. At pi over 2, I have a 1, and at 3 pi over 2, I have a negative 1. And there again, if we see, because of the circular action of the sine at over here, 1 half, 2 half, 3 halves, 4 halves, 5 halves, it's going to be back at 1. Negative pi over 2, it's going to be at negative 1. 1 half, 2 half, negative 3 pi, going to be back at 1. So that's nice. So now I have some clear points. I have some vertical asymptotes with the graph of cosecant, and I have some clear points, some pi over 2, 1, 3 pi over 2, negative 1, negative pi over 2, negative 1. What do we need to do now? We need to figure out, and we know a graph. At an explosion, that's why we call them explosions. At the graph of an explosion, no x-intercepts. The graph has to explode up or explode down. It's got to explode up or explode down. So it's going to have to go up. But let's look at another reason why it goes up. Let's look at the sine values. Let's first of all, and it's going to have to explode down to that point. Well, my question is, why couldn't it do this? Why couldn't it go down and then back up to 1? And why couldn't the relative minimum be between 0 and pi over 2? Why can't that be the relative and then come down here and then come back up? Let's discuss why that couldn't happen. So let's look at the sine between 0 and pi over 2. If I look at the sine between 0 and pi over 2, what happens to the y values? Back to this very first discussion. Between 0 and pi over 2, the y values, the sine values, are doing what? 1 half, square root of 2 over 2, square root of 0 over 2, 1. They are increasing, correct? My y values are increasing between 0 and pi over 2. Completely, they're increasing. Whoop, up to there. Well, what's 1 divided by increasing values? 1 divided by increasing values have to give us decreasing values. By that discussion we had at the very beginning. So therefore, that's nice. So now this has to do this. I want to make sure I'm graphing it in red. It has to decrease to that point. Because the sine was increasing from 0 to pi over 2. The sine was increasing from 0 to pi over 2. So 1 divided by increasing, decreasing. Hey, look at between pi over 2 and pi. What's happening to the y values? They are, Billy, you're right. The y values are decreasing. If the y values are decreasing, 1 over decreasing values, increasing. So back to my graph here, there are the whoops. In like manner, if I look from pi to 3 pi, pi to 3 pi, the y values are getting small, the y values are decreasing. 1 over decreasing is increasing. Where am I at here? Increasing, decreasing. And this is why the graph of cosecant, and I'll let you have the discussion of the rest, but it's all trigonometric functions. They're periodic. The same thing happens. The same thing happens over and over again. Got that? What happens between 0 and pi over 2, cosecant will decrease. This was just the discussion that I just had. So now we have a pretty good graph. We have a pretty darn good graph of cosecant right there. And what do we want to do? From the very beginning, we wanted to, we had to investigate to find the range of this graph. So if you look at that, what is the range of this graph? With the range, what are all the possible y values? Oh yes, yeah, we got it. Very good. All the possible y values is going to be y is less than or equal to -1. Y is less than or equal to -1, and all the y is greater than or equal to 1. No y's between here. So the range is going to be y less than -1, y greater than -1. That's the range of cosecant. What's the period of cosecant? How long does it take for that graph to start to reproduce? Reproduce. Is it pi? Is it pi? No. Is it pi? No. No, it's not pi. Because I have a min, I have a max, so therefore the period of cosecant would be 2 pi. Period of cosecant is 2 pi, and I think we have had a good discussion of the graph of cosecant of x. The period of cosecant of x is 2 pi. That gives us a very nice discussion of cosecant graph. After a while, you will memorize the cosecant graph, but what's more important, I'm not a big memorization guy, can you develop it? Do you remember? Do you remember? Quotient functions.
Stand by the highway.